Hey there. So today I have another cool integral for you, and this time we have a limit of an integral. So it's going to be a crazy ride, trust me. And this problem is thanks to the Instagram page Solving Together, and you can check out his Instagram page. I've linked it in the description, and his solution to this problem is completely different from mine. So if you want to look at an alternative way to solve this problem after you've seen my solution, you can go ahead and check it out. And of course, he posts such cool problems daily, and I can't solve most of them, to be honest, but when I solve them I get a lot of pleasure because most of them are very hard. So anyway, let's get started. So firstly, we have sine x over 1 plus cos square nx, and since n is going to infinity, we can't really do anything about this thing. So what do? I mean, we don't have any formula for cos square of nx, like we do, but they'll be very complicated and we'll end up getting really huge expressions, and this is not really the case in which we want huge expressions. So what we'll do is, firstly we'll simplify this a bit, because if you notice, this integration bound is actually symmetric. And to show you that, basically if you look at the graph of sine x, so this is y equals sine x, this is x equals pi by 2, and this is 0. So we are going from 0 to pi. So obviously sine repeats from 0 to pi. So it goes from 0, it goes up to 1, and then it falls back to 0. And cos square of nx, as n goes to so firstly I'll like to draw the graph of cos square x. So this is just y equals cos square x. So its graph will look something like this. Right, so this is 0, this is 1, this is pi by 2, and this is pi. So this is just cos square x. But if you keep increasing the coefficient of x, so if we make this into cos square nx, then this graph will keep shrinking, right? So if cos square x itself repeats from 0 to pi, then we can be certain that cos square of nx will also repeat. And you can actually prove this with a little algebra, but I'll not do that here. I'll just take it as a given for now that cos square of nx also repeats over this bound. So we can directly write this. So I'll drop the limit part over here. It's implied that n is going to infinity. I'm not going to write that every time. So we'll get twice the integral from 0 to pi by 2 sine x dx 1 plus cos square nx. So that still simplifies the problem, but not quite. So what do we do now? Well, since we don't have any formula for cos square of nx, I guess we'll just have to go ahead and plug in the complex definitions, exponential definitions of sine and cos, because we can't really do anything over here. You can't Taylor expand it because you'll get an infinite summation in the denominator. What do you do about that? And you can't really expand this using a formula, as I said. So the only option we have remaining is to do the complex exponentiation thing. So we'll write this as 2 times integral from 0 to pi over 2, and sine x is e to the ix minus e to the minus ix over 2i dx all over 1 plus, now this is going to be a big one, so e to the nix plus e to the minus nix over 2 squared. So this is what it turns into, and I know it seems really complicated at this stage, but it will simplify, because firstly we can cancel that out, and secondly this 2 will become squared and it will become 4, and since it's in the denominator of the denominator, it will go into the numerator. So we'll get 4, and this 1 over I can actually be taken out as minus I, because 1 over I is equal to minus I. So 4, we have that, and then we can write that e to the ix minus e to the minus ix dx, and don't forget to convert this 1 into a 4, because this 2 just jumped up. So it will become 4 plus e to the 2 nix plus e to the minus 2 nix plus 2 times their product. Well, they are reciprocals of each other, so their product is just 2. Okay, so now what we'll do is we'll get rid of e to the minus ix and e to the minus 2 nix by simply multiplying the top and bottom by e to the 2 nix, because then this will become 1 and this will also go away. So we'll get minus 4i 0 to pi over 2 and then we'll get e to the n minus 1 ix times e to the 2 ix minus 1 dx. You can check if this is exactly what you get, and then you'll get e to the 4 nix plus, so this will combine with this to give 6, and then since we are multiplying top and bottom by e to the 2 nix, we'll get e to the 2 nix over here, and then plus this will become 1. Okay, so this is what we got so far, and I made a slight mistake. Instead of writing 2n over here, I just wrote n, so I fixed that. And now what do we do? Because now this looks even more complicated because the numerator and denominator are both longer, but this is actually going to make everything simpler, and we can't really substitute u equals e to the ix, because then we'll be integrating over a weird path, because then our integral will turn into a path integral over the complex numbers from 1 to I over the semicircle, and I don't really want to go into complex analysis for now because, well, I don't know how to do complex analysis. So anyway, we'll not go over there. We'll just stick to simple elementary integration and no complex analysis required. So how do we do that? So over here, I want you to notice that x is just going from 0 to pi over 2, and that's just a simple interval over the real numbers, which means that the fundamental theorem of calculus applies, which is that if we calculate the antiderivative of this entire integrand, then we can just plug in x is equal to pi over 2, x is equal to 0, and we'll take the difference, and that's our answer. But that won't work once we make this substitution. So how about, instead of making the substitution with the bounds, we'll just forget the bounds and we'll instead calculate the antiderivative. And I know you're going to think that you can't really find the antiderivative of this thing even after the substitution because, well, it's really complicated and you have these n's over here which makes it really hard, so you can't do partial fraction decomposition, for example. And you're right, we can't do that, but we can convert it into an infinite series. We can take its antiderivative, and then once we take its antiderivative, we convert it back into a function of x, and once we convert it to a function of x, we can apply the fundamental theorem of calculus, because it's just an interval over the real numbers, nothing wrong with that. So let's get started. So as I said, we are going to forget about the bounds for now, and we'll just define a function which is f of x equals the antiderivative of e to the 2n minus 1 ix, basically this entire integrand. So now, of course, there are infinitely many functions satisfying this condition because, well, there'll be a plus c in the end and blah blah blah, but we don't really need to worry about that right now because we are anyway going to take the difference of f of pi over 2 and f of 0, so the c's will cancel out as usual, so we don't need to worry about all those nitty-gritties. So to make our life simpler, what I'll do is I'll make this equal to L, and of course n is going to infinity, and we can say that this is f of pi over 2 minus f of 0, and just by making that statement we can forget about the plus c. So let's get started and let's try to do something with this monster. Okay, so I made another mistake. This is supposed to be this entire thing into minus 4i. So I know it's really cluttered, but I hope you get what I mean, because this is right over here and we didn't really include the minus 4i over here. So now let's get started with dealing with this. So as I said previously, a substitution of, let's say, t equals e to the ix will simplify this greatly. And right now, since we are not worried about the bounds and we are not worried about integrating over a path, we are just making a substitution to try and figure out the antiderivative, and in the end, once we do figure out the antiderivative, we are going to undo all the substitution, so we don't need to worry about complex analysis. So now we can just do the usual substitution and just consider this as substituting t is equal to e to the kx. So it's just a usual substitution. So we get dt is I e to the ix dx. So now we don't have the I over here, so I'll just multiply and divide by I, and 1 over I is minus I, so I'll make it that. So minus I, and then this is t to the 2n minus 1, but remember that we used up one of the e to the ix's over here for dt, so this will just become 2n minus 2, so t to the 2n minus 2 times t square minus 1 dt over t to the 4n plus 6 t to the 2n plus 1. And now if you're familiar with what exactly happens when you substitute, let's say z is equal to 1 over t, then your heart will be screaming to separate this integral into a difference of two integrands using this right here, and then substituting z equals 1 over t in one of them. So let's go ahead and do that. We get minus I integral t to the 2n t square and this combine, or dt all over t to the 4n plus 6 t to the 2n plus 1. This is really a tongue twister, my bad. And then plus I integral, and then this will become t to the 2n minus 2 dt over t to the 4n plus 6 t to the 2n plus 1. And in case you don't see why we are doing that, you'll see in a moment. So if you make this substitution, we actually have dz is equal to minus dt over t square. So we can actually multiply and divide by minus 1, so this will become minus and minus, so I'll put that in brackets, and we need 1 over t square, so let's multiply and divide by 1 over t square. So this will become minus dt over t square, and if you divide by t square, then you're basically divide by 1 over t square, you're multiplying by t square, so that will make this into t to the 2n. And now we are perfectly ready to make the substitution. So this entire thing is just dz, so we can write that entire thing. I'll just put the brackets like that, and then minus I integral of. Now I want you to be careful, because z is equal to 1 over t, so this is 1 over t to the 2n, this is 1 over t to the 4n, so sorry, z to the 4n, so this z to the 4n will jump up, it will cancel out with 1 over z to the 2n, and it will leave out z to the 2n on top, dz, and then this will become 1, and then this will become z to the 2n, so 6 z to the 2n plus, and this will become z to the 4n. But now notice that you just have t over here and z over here, but the integrand is the exact same. So this is, if you call this entire integral, let's say g of t, then this is g of z. So what this means is, if we just deal with this part, then this part will automatically be dealt with, because the antiderivative of this is exactly the same as the antiderivative of this. So all we got so far is written down over here, and now what we'll do is we are going to be partial fraction decomposing this entire integrand. So for that, what we'll do is we'll just treat t to the 2n as, let's say, some new variable y. So I want you to remember that this is not a substitution. We are not going to substitute this over here and then do the integration in terms of y. We are just doing this for the sake of partial fraction decomposition. So let's get started. We get y over y square plus 6y plus 1, and we can actually factorize this pretty easily. It's just a simple quadratic. So I'll complete the square, and if you complete the square, you are going to get plus 3 square minus 8. So from here, since we've completed the square, we can factorize this by using a square minus b square is equal to a minus b times a plus b, the identity we all know and love. So from here we get y over y plus 3 plus 2 root 2, because the root of 8 is 2 root 2, and then this times y plus 3 minus 2 root 2. So if you do the partial fraction decomposition, this is what you get. So now let's move on. And now what do we do? Well, as I said previously, we want to convert this into an infinite summation. So how do we convert this into an infinite summation? The first thing that comes to mind is GP. So I want you to firstly remember that mod t and mod z are both 1 for all x. So any value of x, any real value of x which you choose, mod t and mod z will both be 1. So what we can basically do is, we can take 3 plus 2 root 2 common from the numerator and denominator over here. So this will become 1 and this will become y over 3 plus 2 root 2 plus 1. And we can't do that over here because 3 minus 2 root 2 is actually less than 1. So if we take this common, then y over 3 minus 2 root 2 will actually be greater than 1. So the GP formula won't apply. So over here what we'll do is we'll take y common from the numerator and denominator. Because this is less than 1, so mod y is equal to 1. So this over y, the mod of this entire thing will be less than 1. And then this will become 1 and this over y. So what does the GP formula say? Well, the version which we are going to use over here is that 1 over 1 plus x is equal to the sum as k goes from 0 to infinity of minus 1 to the k x to the k. So if we apply that over here, then what we get is 1 over 4 root 2 times the sum as k goes from 0 to infinity of, over here x is y over 3 root 2, so minus 1 to the k y to the k over 3 plus 2 root 2 to the k. And for this we'll get plus 2 root 2 minus 3 over y times, this is our x, so times 3 minus 2 root 2 to the k over y to the k. And I forgot the factor of minus 1 to the k. Okay, so far this is what we got, and I've actually made some simplifications by using the fact that 3 minus 2 root 2 and 3 plus 2 root 2 are reciprocals of each other, and I've also changed the bounds over here. So see if you can notice why that change is fine. So now let's get started with the real stuff. So now, since we substituted t to the 2n is equal to y, we can do a similar thing by substituting z to the 2n is equal to u, and since 1 over z and is equal to t, we can say that this is equal to 1 over y. So since u and y are reciprocals, 1 over y to the k is just u to the k, so we can just put u to the k over here. And now I want you to notice that if you want to do this, so this entire expansion was for t to the 2n. So if you want to do a similar thing with z to the 2n, all you really need to do is replace y by u and u by y, and you'll have the answer. So in the end we'll get that f of x is equal to minus I over 4 root 2 times, and this is going to be a really complicated expression, but it will get simplified pretty soon. 3 plus 2 root 2 to the k, and now notice what I do. I'll write y as t to the 2n, so we'll get t to the 2n k dt plus z to the 2n k dz. So I want you to notice that all I've really done here is I've used the linearity of the summation and the integral, and I also want you to notice that you'll usually see such an expression while doing line integrals in multivariable calculus. So I've borrowed that notation for now and I'm using it over here, but you need to remember it's not a line integral, and all I've done really is I've used this fact, and we are still missing one term, which is this summation. So we'll get plus integral k equals 0 to infinity minus 1 to the k, over here we'll start with k equals 1, so 3 plus 2 root 2 to the k times dt over t to the 2nk plus dz over z to the 2nk. So I know that this looks really complicated, but I want you to notice that all of this is just constant. So we can actually take the integral sign inside like that, and same thing over here, can take it inside, and this is just the power rule. So this just becomes t to the 2n k plus 1 over 2n k plus 1, and similar thing over here, z to the 2n k plus 1 over 2 nk plus 1, and of course the integration sign goes away, so I'll just do that. It's becoming really messy, I know. So now what do we do with this? Well, firstly notice that it's a negative power, so when you integrate it you'll get a negative coefficient. We can just make this into minus, and then we can do a similar thing over here. So since we already took care of the minus sign, we'll just get 1 over t to the 2n k minus 1 times 2nk minus 1 and plus this will become 1 over z to the 2nk minus 1 times 2nk minus 1. And now finally we are going to be using the fact that t and z are reciprocals. So this is going to get really simplified now. So k equals 0 to infinity minus 1 to the k, 3 plus 2 root 2 to the k, and this will remain the same. So I'm just going to draw brackets like that, and I guess I'll separate these, and then this summation will get simplified quite a lot, because notice that 1 over t is z and 1 over z is t. So we can get minus 1 to the k, 3 plus 2 root 2 to the k times, and now this will become, and actually I'll take this constant factor also outside the bracket, so 2nk minus 1, and then this will become z, so z to the 2nk minus 1 plus t to the 2nk minus 1. So it took me an eternity to get the board ready for this shot, and this is finally what we got so far. And now we are finally ready to plug in the bounds, because we found out f of x in terms of blah blah blah, and we can just now put in x is equal to pi over 2 and x is equal to 0, and it's going to be easier than you think, because notice that if you put x is equal to 0, then t and z are both 1, because they are just e to the 0 and that's 0. And I also want you to notice that x is equal to pi over 2 implies that t is equal to e to the I pi over 2, so that's just I, and z is equal to minus I. So let's substitute these in here. So now I want you to notice that z to the 2nk plus 1, so well 2nk plus 1 is an odd integer, so we are basically talking minus I to the odd power, and we are adding to that I to the odd power, because again 2nk plus 1 is odd. But notice that this is basically I to the odd power times minus 1 to the odd power, and well, what's minus 1 to the odd power? It's just minus 1. So we just get I to the odd power minus I to the odd power, so that's just 0. So for x is equal to pi over 2, this entire thing becomes 0, and you'll see a similar thing over here as well, because 2nk minus 1 is also an odd number, so over here also you'll see a similar cancellation. So we'll just get f of pi over 2 is equal to 0. How nice. And then f of 0 is not very much harder either, so we'll just get 2 over here and 2 over here, because both of them are 1. So so I'll just do the editing over here. This will become 2 and this will also become 2. But now I want you to notice that since n is going to infinity, in the very beginning we wrote limit as n goes to infinity. So as n goes to infinity, each and every term of this summation goes to 0, because n is in the denominator and there's nothing to cancel it out. So for each and every term, as n goes to infinity, each and every term goes to 0, and the same thing over here, same thing happens over here. And this is not the integration case. You won't get 0 plus 0 plus 0 so on is non-zero. You'll just get the entire thing is 0, because each and every term is a solid 0. And similarly you'll get the same thing over here. This will also become 0, and remember that we are talking about f of 0. But notice that we made a careless mistake over here, because the k equals 0 term, in that this term will basically vanish, so you'll just get 1 in the denominator, which means that the k equal to 0 term will not become 0. Every term other than k equals 0 will become 0. So let's see what this entire thing evaluates to if k is equal to 0. Well, this is 1. This will become 3 plus 2 root 2 to the 0, so that's just 1. This is also 1, and this is 2. So the entire thing is just 2 times 1 over 1 times 1, so that's just 2. So this is not 0, this is 2. And now we can fill in what goes over here. F of 0 is equal to, this entire summation is 0, there is no exception in the terms over here, you can check for yourself. Over here there is one exception, and that is k equals 0, so this entire thing evaluates to 2. So 2 times minus I over 4 root 2, that gives us minus I over 2 root 2. So now our final answer is minus 4i times f of pi over 2 is 0 minus f of 0 is minus I over 2 root 2, and this evaluates to root 2, which is our final answer. That was quite the ride, wasn't it? So now go ahead to the Instagram page of Solving Together and check his solution out. It's completely different, I promise. I hope you enjoyed. Thanks for watching.
Turn up. Let's go.